This is Mike Arnold's AR-5. It's 14.5 feet from the tip of the spinner to the tail and a little over 21 feet from wingtip to wingtip. It's mostly made of fiberglass and epoxy over styrofoam. The airplane was made entirely without molds. The engine is a completely stock 582 Rotax 2-cylinder liquid-cooled two-stroke with a gearbox. When it's working right, it puts out about 65 horsepower. In August of 1992, Mike surprised the experts by setting a new 3-kilometer world speed record for airplanes weighing less than 661 pounds gross. (213.18 miles per hour). Mike started the design in August of 1981, exactly 11 years before he eventually set the record. It takes time. He wasn't in a real big hurry. This is the little town of Crockett, a half-hour north of San Francisco. He moved here in 1978 from the Mojave Desert, where he'd been learning to design and build with aircraft composites at Fred Duran's glider repair station out there, with Burt Rutan on the Mojave Airport. He rented a small shop right in the middle of this quiet little community. The building he found used to be a restaurant with a boarding house up above. Most people had no idea what he was up to in there. What he was up to, of course, was making airplanes. Mostly Rutan designs for other people. First a Very Easy, and then the Amsoil Rutan Racer. That's it in the foreground. It went on to set a world record in 1982, and then demonstrated the unusual strength of foam and fiberglass construction by smacking into the desert at Reno at 200 miles per hour. It's tough material. The pilot walked away from this one. Mike has wanted to design something like this since he was a young boy. In this article about his models, he describes an airplane with dimensions remarkably similar to the AR-5's. It was to be powered by a lawnmower engine. It was a long time before he finally got around to doing it. What he'd always wanted was a cheap, high-performance dogfighter. He made models to investigate lots of different configurations and engines and cowls, and even looked at retracting the landing gear. Not worth the effort, he concluded. The airplane first flew in March of '91. It handled beautifully right from the beginning, and seemed fast. It had all the usual teething problems of a new design. Mike tried a spinner and wrestled with the cooling system, and tried 5 different propellers, and changed the ratios in the gearbox and rejetted the engine until he finally got it to go 207 miles an hour in level flight. He knew the world record at the time was 201 miles an hour, so he called the National Aerodynamic Association in Arlington, Virginia, to see how to go about setting up a new world record attempt. A couple of months later, and a few $1,000s poorer, he knew all about it. The first thing he had to do was establish the weight of the airplane with pilot and fuel on freshly certified scales. These particular scales belong to the State of California Department of Weights and Measures, and these volunteers came out on Saturday to help out. The maximum allowable weight in Fédération Aéronautique Internationale Class C1AO is 300 kilograms, or 661 pounds. The empty weight on Mike's airplane came out to 488 pounds, which didn't leave much extra for pilot and fuel. And fuel was a big concern. The weighing has to be observed by National Aeronautic Association officials. That's Tom Gribben with the baseball cap and Jack Sweeney with the beard. The last record they did was Lyle Shelton's Bearcat at 537 miles per hour. They explained the rules and specifications for a world record attempt, and they told Mike how to set up the course. Jack helped arrange for 6 timers to come out from the National Air Racing Group to help on the record attempt. All these folks do this for fun. A nice bunch of people.
Well, okay, then let's lock it up here.
When the Yolo County Weights and Measures official finally totaled up the numbers, he certified that the AR-5 was 0.8 of a pound under the 661-pound limit with pilot and fuel. The airplane was sealed, certified, and locked in the hangar, and everybody was happy. Now it was off to see the course. Mike had located a little used road in farm country near the airport and had a surveyor come out the day before to stake the course, so all that was left to do was find the stakes and set up the white PVC pipe poles that served as gates on the course. That's Mike's dad, Harry Arnold, in the green shirt, and his boyhood friend Norm Justice, who served as an altitude observer. They made all the gates for the course. And this is an altitude observation station. There's one of these at each end of the course. The observer, by sighting past the nail on the top of the gate, can make sure Mike is under the 500-foot ceiling required by the rules when he passes the outer boundary marker. They put these outer boundary markers a kilometer ahead of the timer stations in order to bleed off any extra speed the airplane may have picked up diving before it gets to the time section. It's just to keep everybody honest.
Okay, let me explain what we're going to do out here. I'm going to draw the ground here. The rules say that the course has to be 5 kilometers long. There's 1, 2, 3, 4, 5. And they're very specific about the fact that over the full 5 kilometers, I have to be under 500 feet here. Under 500 feet. Same thing down on this end, under 500 feet. And throughout the whole course, from takeoff to landing, throughout the whole flight, I have to be under 1,600 feet here. And in order to keep me under 1,600 feet, I'm going to have a couple of guys alongside of me in airplanes, making sure that I don't exceed 1,500 or 1,600 feet from the takeoff to the landing. The outer markers, this point here and this point here, are going to have observers to make sure that I don't exceed the 500 feet when I enter the course. The first timing station will be right down here, and it's a timer. And there's another timer right down here. So what I'm going to do is I'm going to come in probably at about 1,500 feet here. I'm going to dive down, pick up speed, and just to make sure that I don't foul out, that I don't exceed the 500 feet, I'm going to come in at about 350 feet here. And all the way through the course, you'll see me descend, descend, descend until by the time I reach the last timing station here, I'll be down around 20 feet. Then you'll see me come back up again, and I'll go back up to 1,600 feet and turn around. The rules say that I have to make 4 consecutive runs, down, back, down, and back. I don't have enough fuel to make any more than 4 consecutive runs, so that's another reason for me to be very conservative when I enter the course here, make sure I don't foul out. And let's see if I've forgotten anything. I think that's about it. So Norm, you're going to be down here on this altitude observation station. Dave, you'll be over here on this one, and the timers will be here and here, and we'll go out and take a look and see where those are.
They were right where they were supposed to be. That's Mike's friend, Dave Rourke, a fellow airplane builder who helped in many ways throughout the project. The timing stations themselves were set up 3 kilometers apart. It took all afternoon, but that's all there was to setting up the course. Everyone finally went home, and Mike checked over his permits one last time.
So what I've done is I've got the approval of the Yolo County Board of Supervisors, the Colusa County Board of Supervisors, and the County Public Works Department Supervisor, the Williams California Highway Patrol Office, the Yolo County Sheriff's Office. We've talked to the local crop duster out there to make sure that we don't get mixed up with him. The FAA has approved our overflying the course at under 500 feet. It was a big deal. They wanted
everything was a big deal. Everyone wanted a letter or a topographic map or a permit from someone else. Mike said he felt like he was trying to get permission to test an atomic device out there, but he finally did get to sleep that night.
Map. Oh, hey, yeah, let's have a copy of that for that. You got a copy of that for this?
Yep.
Yeah. You take one and you got one, or whoever you got for the other.
Now, after each pass,
Jack Sweeney is briefing the volunteers from the Yolo County Sheriff's Air Squadron, who gave up their Sunday morning to come out in the wee hours and block the road. Mike found that all government agencies he eventually wound up dealing with were very cooperative once he had all the proper permits. The C1AO world record was held, at the time, in Austria by a fellow with a BD5, and everyone was pretty keen on the idea of trying to bring it back home to America.
Ready. 3, 2, 1, go.
Jack is the National Aeronautics Association's 3-kilometer specialist, and although his official responsibility was only to observe, he and his wife Sylvia actually wound up running the timing of the attempt, in addition to all the help they provided setting up the course.
71.
That'll do it. That'll do it. The magic numbers. Okay, guard the buttons with your life, and we'll
do not push any of them.
With all their clocks synchronized, their radios tuned, and their donuts and coffee, the timers caravan off to their stations on the course. In the meantime, back at the airport, Mike is all strapped in and waiting nervously for the temperature on the course to come up a little. He's discovered over the last couple of weeks that his speed is greatest when it's around 75 degrees, and he's asked Kit Sodagrid to station himself over the course in his midget Mustang to call the temperatures and conditions back to him. The only problem is, Mike can't hear him, so his dad takes off with one of the NAA observers in his Thorpe T-18 to go relay messages from Kit back to Mike. They don't want it to get too warm because the bugs come out and slow him down, and the engine runs hot, and it's already getting warm. Mike's starting to think how difficult it would be to set this whole thing up again for another day, and the queasiness and butterflies set in. Finally, Kit calls to say it's 75 degrees on the course, and he's starting to get some bugs, so if he's going to do it, he better come on now. And the record run is on. Tom Gribben follows Mike out in his big Cessna. Tom is a surveyor by trade, and he's the one who gives final approval of the course for the NAA. He and the other observer with Mike's dad will monitor Mike's altitude during the flight.
No, that's the mini Mustang out there.
Okay, this is Mike. We're about 3 minutes from our run here. 2.5 minutes from our run.
Okay.
Okay.
Let's let Mike take it from here.
Craig Cato's beautiful racing propeller has so much pitch on it that the initial takeoff roll in the airplane is very sluggish. It doesn't really wind up enough to develop any real horsepower until I'm doing well over 100 miles an hour. Then it'll climb 1,100 feet a minute, but it's not real exciting below that speed. Once the tail comes up, it starts to accelerate pretty well, and it doesn't take too long for me to get up to 60 miles an hour, my normal rotation speed. I'm trying to conserve fuel here, so I pulled the power back to about half throttle. It doesn't really make that much difference in the initial rate of climb anyway. And I set up a cruise climb and head straight out for the course. It's very smooth air this morning. I noticed right here that my legs were feeling kind of weak. But otherwise, the airplane was running great. Here comes Tom Gribben in his Cessna, following me out. It's about 12 minutes out to the course from here.
If he was high, we would... Lord, be quiet.
I hear him. There he is. He's right over the wires, heading towards us.
I got him.
There he is.
You got him, Sue? Okay.
I got him.
takes a little over 31 seconds for me to get from that first timing station to these guys 3 kilometers down the road. And it's a hard little airplane to see, as you can tell, especially coming out of the sun like that. We later calculated the speed on that run at 212.57 miles per hour. Everything in the airplane was looking good, so I turned around and came back through again.
There he is. Yeah. Right down on the deck.
You guys still back there?
He's way low, yeah.
I can. Right. Yeah. Okay. Stop. Ready.
God, you make a good Formula pilot.
Dave, you mighty quiet back there.
That run came out to 214.98 miles per hour. We might have a little tailwind in this direction. .90. Everything's still looking good, except one of the altitude monitor's radios has gone out, and I don't know if I've been entering the course low enough. The final pass worked out to 213.29 miles per hour, and it's finally over. My knees are still shaking. It's been confirmed on the way home that all the runs have been under 500 feet, so I really don't have to worry about that one. But I do have to worry about whether they've been fast enough, and we're not going to find that out till we all get together later in town to crank out the numbers. The weather today has been just about perfect. Very few bugs on the course and just a little hint of a breeze. We really couldn't have asked for more. That doesn't mean, however, that I'm still not very anxious. It's taken 2 months to set this whole thing up, and anything can happen. And I'm not going to feel easy about the thing until I see those final numbers.
Oh, I'm glad that's done. Better for worse. Yeah, now we have to wait and see.
Everything seemed to be running fine, though?
It was running good. I was so distracted by some problems we were having communicating with the boundary markers on the course that I made a couple of terrible runs.
Oh.
But I just didn't have enough fuel to make it up.
Right.
So we'll see. I think I could have done better. Maybe next time.
It seemed to take forever to do all the calculations necessary to get the averages of the 4 runs. But Jack was very careful and precise. This was a world record attempt after all.
It's not the official speed, it's official enough to know you're within a mile or two of that.
Oh, I love it. I love it.
Yeah, you can announce it.
Thanks.
213 miles an hour. Thank you very much. Well, it's as far as I know, it's 240 square feet. And
I started to write an article for Sport Aviation magazine soon afterward, and I called some aerodynamic experts for help in describing the airplane in technical terms. What I was trying to do was define what the airplane was doing aerodynamically. I'd never done any drag calculations on the AR-5, or any drag calculations, period, and I was kind of stunned when I finally worked them out. The drag numbers I was getting were very low, and these experts were telling me I'd broken something called the magic 1 square foot barrier, and apparently no one had ever done it before. It referred to the equivalent flat plate drag area of the airplane, and mine was way below the magic square foot. I hadn't heard of the square foot barrier, but all 8 of the experts I wound up calling had heard of it, and they all thought it was an amazing accomplishment. One of them, who came out to examine the airplane, was so amazed he was convinced it was some kind of hoax. He said I couldn't have done it. But then Mr. Bruce Carmichael came out to take a look. Throughout his distinguished career as an aerodynamicist, Bruce has had a special interest in low-powered, low-drag, laminar flow airplanes, and he was very helpful on this. He did a lot of calculating for us, did a complete drag breakdown on the airplane.
Okay, what do you want to do next?
There seems to be some controversy about this drag area. There has been some speculation among designers around the country, at least 2 that I'm aware of, who have predicted that no one was going to be able to get below a square foot of drag area, or that they weren't aware of anyone who had gotten below a square foot of drag area. This airplane is well below a square foot of drag area. And I've been telling people that the airplane has the lowest drag of any airplane in the world that we know about. Is that an outlandish assumption?
Yeah. On drag area, I do not know of any calculated numbers on drag area that are below 1 square feet. It's very possible that the latest Formula A racers, like Bubber's Bullet and the Nemesis,
Formula 1 racers,
it's possible that those racers are getting close. That was always the goal. Could we make a man-carrying airplane of any type that would have as low a drag area as 1 square foot? Because that is the product of the size of the airplane and its cleanliness. But now it'd be kind of nice to know, what do we know about cleanliness? You know, separate from the fact that it's a small airplane. Take the size out of it, and then we could even compare it with fighters and transports and jet airplanes and everything else.
But you have a way to do that.
And there is a way to do that. And all you got to do is, since the drag area has the units of square feet, all you got to do is divide by a significant area of the airplane in square feet. And the best one to do, in the old days, everybody divided by the projected wing area. But that isn't fair, because the number you get is a function of how big the fuselage is compared to the wing, for example. So the right number to use is the total wetted area, every bit of the surface of the airplane that the air is scrubbing by. And you and I got a pretty good guess of or a good calculation of what the wetted area of the airplane is. Okay, when I take these same assumptions on the horsepower and on the propeller efficiency, I get these wetted area coefficients all the way from 00363, the lowest value with the low propeller efficiency and low power, up to about 004 on the higher power and the higher propeller efficiency. Well, what does that number mean? What can we compare it with? Okay, we're talking about a propeller-driven airplane with cooling drag problems. And there was an airplane once, the P-51 Mustang, and the reason it was made that long range into Germany, in fact, not only was because of the drop tanks, but because it had a very low drag configuration. Although it had low drag airfoils, very similar to what you've used here, with the metal construction, they really weren't getting the help from laminar flow. But they were faster, bigger airplanes, so the Reynolds number was higher. This helps bring even the turbine boundary air drag value down. But the other thing they had going for it was that they had worked out a cooling system where they had either zero cooling drag or a little bit of thrust. That airplane has a wetted area coefficient, including the cooling drag, of 004, which is the size and number that you're a little below. And from our best estimates.
Has less drag than the P-51.
Yes, in spite of the fact that you obviously got cooling drag.
And I have a fixed gear hanging.
And you've got a fixed landing gear, yeah.
Okay, all of that happened, of course, a couple of months ago. Here we've got the airplane back in the shop. I've had a chance to think about all this stuff. I'm not sure I know any more about it than I knew before I talked to the experts, but it was all great thrill and lots of fun. let's see if we can go through it now and see why, in retrospect and with the help of the experts, the airplane goes so fast. First thing you'll notice here, of course, is that the airplane has had a little mishap. The propeller, oh, my record-breaking propeller. Craig's going to be real upset with me. We'll talk about all that stuff later, though. When Alex first came in to look at the airplane, the first thing he wanted to look at was this propeller. And the first thing about it that he noticed was that the ratio between the diameter and the pitch, which turns out to be 1.5 to 1. This is a 50-inch diameter by 70-inch pitch, almost 1.5 to 1. Turns out to be absolutely optimum. Craig, Cato, and I didn't know that at the time, but that's one of those little lucky things. The next thing that everybody noticed was this cowl. They all said it's a great idea to make it round like this. This is a real good idea. But you'll notice from the earlier shots that the cowl was originally intended to have that great big red spinner that you saw. This spinner, we spent a lot of time designing the airplane, the cooling system around this spinner. One of the things that happened when we first flew the airplane with the spinner was we discovered the spinner didn't want to stay on the airplane. It kept vibrating. This engine's a real shaker. So one afternoon we tried it. We flew the airplane without the spinner, and we're very surprised to discover that the airplane was just as fast without the spinner as it was with it. The experts have all told me, I didn't know this either at the time, that the spinner, the absence of the spinner is no problem because the air builds up, the pressure builds up in the front here, and the air forms its own fairing around here. As long as the sides of the opening are very smooth like this, and as long as they have a nice round lip up here, it makes no difference whether there's a spinner or not. This smooth shape here also contributes to good laminar flow all along the back of the cowl here. And as long as we're back this far, the next thing the experts told me about was the good position I put the cooling air outlet. It turns out that the best place to put it is that part on the cowl, or right behind the cowl, where it has reached its maximum width, where the two sides here are parallel with one another. It's a low pressure area right in here, and of course that's just where you want to let cooling air out of, into a low pressure area. Fuselages in general, of course, you can reduce the drag on just by trying to make it as small as possible. The dimensions on this fuselage and on fuselages of any airplane this size are pretty much determined by the size of the pilot. This dimension from the top of the canopy down to the bottom of the airplane is determined by my height, sitting in that position, in that seating position that I decided to sit in. The length of the fuselage, especially from the center of gravity forward, is determined by the distance forward that I had to put this very light engine to get it to balance. And the length of the fuselage from the center of gravity back to the tail is determined by the amount of lever arm that I determined I needed to take care of this rather large wing here. So to get the control force I needed on the tail, this dimension had to be what it is. To get the airplane to balance from the center of gravity forward, we had to have this dimension. So there's not too much I could do to reduce this unless I wanted to lay down in the airplane. Then I'd have problems seeing out, of course. So, okay, and that pretty much takes care of the fuselage. Let's take a look at the wing. This is the first thing you notice about this wing is that it's very thick. It's a 65 old NACA profile, 65 series. It's a 418 at the root, going on out to a 215 at the tip. The reason I made the tip airfoil have less camber than the root was that I was trying to simulate the span-wise lift distribution of a more tapered wing. You'll notice that this wing is not very tapered, and I did that for a couple of reasons. The first is that If I reduced the taper on the wing, I got to make it shorter in here toward the root, toward the fuselage. That helped me do a little trick that I'll talk to you about later in terms of interference drag reduction. The wing is also a very high aspect ratio for a sport plane. It's an 8-to-1 aspect ratio. That helps in terms of reducing the interference drag at high angles of attack in climb or in takeoff. It allowed me basically to use this little two-stroke engine, which has a very low power band, a very narrow power band, and very low torque at low RPM. So where you really suffer with a little engine like that is trying to take off and climb. So high aspect ratio helps in that very much. The wing is a thick wing. It's 18% thick because I was looking for stiffness and lightweight. If I made the wing thinner, I'd have to put a lot more material in it to make it as stiff as a wing that's thicker. So that thickness is good for the structural considerations, but it's bad for speed. So I could make the airplane go faster by making a thinner wing. The wing is also quite large. The area is 56 square feet. That's to keep the stall speed down, to make the airplane handle well at low speeds, and of course I could make the airplane much faster if I made that wing area smaller as well. Didn't do either one of those things. The wing is a laminar flow wing, what they call laminar flow. All wings, incidentally, are laminar flow back to a certain point. What airfoils that are called laminar flow are really just extending the laminar flow back a little farther than it would be on a normal airfoil. The wing surface is fairly smooth and nothing really remarkable about the surface. Wait a minute, that's not quite true. I hadn't checked it with a wave gauge yet. Wave gauge is a neat little instrument. It's just an old-fashioned dial indicator mounted to an aluminum block with 3 little legs sticking down. It's set up so that by moving it along the wing surface, you can detect even the most minute little bumps and dips. It's very accurate. This particular one belongs to Bruce Carmichael. He's used it a lot on sailplanes. I don't believe I've ever seen one used on a power plane before. Smoothness is so important on sailplane wings because they use the same kind of long laminar run airfoils I've used on this airplane, and these airfoils just don't work if they're not smooth.
Okay, that's got it. Oh, this is very good.
Is it?
Yeah.
Oh, look!
Now, what you have to remember is that we have expanded the vertical scale here. Let's see now, this is 10 units here is an inch, and 10 units here is 2/1000ths of an inch.
So we're exaggerating
it. 500 times the vertical scale is exaggerated compared to the horizontal scale.
Can we put that down here, Bruce, so we can take a look?
Now I'm going to draw some mean lines through and we'll look at peak to peak.
So that is an exaggerated chart showing the waviness.
That's 500 times lumpier than the wing?
Yeah, right.
500 times lumpier than the wing actually is.
Yeah. Now where we see this biggest joggle through here is in your spar location, and that's where it's hardest to keep the...
Just about where I'd expect it.
Yeah. Now if we look at peak to peak, see we've got this much is a 1/1000th of an inch. So we're coming up here peak to peak. We've got 1, 2, 3, about 3 3/4 peak to peak. Wave at that point.
3 3/4 thousandths.
Yeah, and this one is 3 3/1000ths peak to peak. That means that put a mean line through, you've got about 1.5 parts in 1,000 ripple in the wing, which is what the racing sailplane pilots work all winter to get their wing waviness down somewhere close to this.
Really?
But most of them will quit rubbing when they are peak to peak 4/1000ths of an inch.
And this is
or
peak
more.
to peak?
This is peak to peak 3 here at this point. And that is very, very low waviness. I've seen our experimental shops at Rockwell work weeks to build a research model for a wind tunnel or a water tunnel and reduce the waviness to this order. Somehow you did it in your home workshop.
Boy, I got lucky.
Well, it wasn't so much luck. I sanded on it for 3 solid months.
And that just about takes care of the wing. Let's go back and take a look at the tail. There's not too much you can really say about the vertical and horizontal stabilizers, except that they're very large. They're large mainly because of that business I talked about the how much we had to move that light engine forward to make it balance the airplane. All of that area forward of the center of gravity is destabilizing. So when you do that, you have to, in order to make the airplane stable again, you have to increase the size of the vertical and horizontal stabilizers. I could accomplish the same end by moving the vertical and horizontal stabilizers back by lengthening the fuselage, but that would of course add weight in the fuselage. The extra area that we picked up in the fuselage, lengthening it, would also create drag. So it's hard to say that that would actually make the airplane go any faster. The profiles, the airfoils I used on all of these surfaces are laminar flow airfoils. I stole an airfoil from Mr. Wortman. These are sailplane profiles. And that's about all I can say about this stuff here. Can't be much smaller or the airplane wouldn't be stable. All of this brings me now to the point where we can talk about one of my favorite subjects, interference drag. That's something that occurs right down in the wing root here. What I thought I knew about interference drag when I started this whole thing was that it was something that happened in the corners of things, something that happened right down in where two sides met. Like, for example, these two sides here. I understood it to be something that happened with the boundary layers from the two surfaces getting mixed up in the corners and sort of beating themselves up and wearing themselves out, so that somewhere downstream here they would separate or transition from laminar to turbulent flow earlier than they should. I thought that until I read an article by Mr. Raymond Parker in one of the aircraft design manuals that the EAA Association puts out. Mr. Parker was talking about interference drag reduction in a way that I had never heard before. Take a look at this. Mr. Parker worked with Gus Raspet at the Mississippi State University. They are a very famous program there, and they were working on sailplanes. This is an airplane built by Mr. Parker, and they modified the airplane by changing the top of the fuselage here and by moving the canopy around and doing all kinds of other stuff. But you notice there's no fillet in there. They're not talking about the kind of interference drag that I knew about. Take a look at this other picture over here. This is what the airplane looked like when it was finished. You can see that they put a little bubble canopy up on top, and they cut the whole top of the fuselage down over the top of the wing. And they also made the fuselage thicker back toward the trailing edge of the wing. I didn't know what in the world they were talking about. I knew it was important stuff because they say it's the most often made mistake in aircraft design. That is something that you do wrong at the wing root. And I also had heard stories from Irv Culver about an airplane that he had worked on that had such bad wing root interference drag that the airplane wouldn't get off the ground until Irv came along and made a special fairing for it. But I didn't know how to make that fairing. I didn't understand the theory. What kind of interference drag is this? I spent a lot of time trying to answer that question by looking through Horner. One of the things he talks about are what happens when you put a couple of struts like these in the wind tunnel. These happen to be off the landing gear struts on the AR-5, and they also happen to be about 5 chord lengths long, each one of them. Total of 10 chord lengths if we put the two of them together like this.
Remember that, because we'll talk about that in a little bit. Horner says that if you put one of these things in the wind tunnel and measure the amount of drag, let's just arbitrarily say it's about a pound of drag on one of these. The other one you stick in a wind tunnel, it'll be about a pound. And if you stick them then both in the wind tunnel, you should get a total of 2 pounds of drag. Well, that works until you start to move them a little closer together. When you get them about this close together, the drag is starting to go up considerably. Not just 2 pounds, but something like 3 or 4 pounds. When you get them close enough together so that they're about a half of a width apart, the drag triples. 6 pounds of drag instead of 2 pounds of drag. Now what in the world is going on there? Let's take a look at the blackboard and see if we can figure it out. What Horner says is going on, here are the 2 struts here. Horner looks right in this area right here. And what he notices is that what we have here is a sort of diffuser. These 2 sides are getting wider as they come out toward the bottom. And Horner notes that as the 2 struts move closer together, let me draw this side here as if we've moved them in closer together, that the expansion ratio, that is the distance between here and here compared to here and here, gets greater as the strut moves closer. Let's see what that looks like. We've got one length here, we've got about that length down here, another one down here. It looks like about an expansion ratio of 2.5. When we move the strut in this close, we have this distance here, 1, 2, 3. Sure enough, the expansion ratio here is about 3.5 to 1, and here it's about 2.5 to 1. Now, what he also notes is that as the expansion ratio in this thing that he calls a nozzle, you see that? You see the nozzle in there? That's what we've got, a nozzle. That as the expansion ratio in this nozzle becomes greater, the drag goes up. Well, very interesting. What could you do to fix that? Well, one of the things that occurs to me that you could do is make one of these sides straight. That would sort of reduce that expansion ratio. There it's 2 to 1. Well, yeah, how would you do that? Bring this side in there, bring this side. We're not making a biplane here anyway, so we really don't care about that. But keep that in mind. We're going to talk about something else now. Okay, here are these 2 little struts again, the 1 pound drag struts. And in this little experiment, Horner puts the 2 struts together to form a T, and puts the whole unit in the wind tunnel, and discovers that the drag, just by putting these 2 things together, has doubled. It's now, instead of 2 pounds, it's 4 pounds. So that means that something down here in this intersection is causing as much drag as the 2 struts themselves. Now what's going on? Horner, by this time in the book, has stopped referring to nozzles, but I see a nozzle right back here. Can you see that? Right back from the point of maximum thickness on the airfoil here, back to the trailing edge, it expands just like that nozzle. As a matter of fact, if you look at it from the side here, you can see that it's expanding in 2 directions. This side's falling off as well as this side, so it's expanding in both directions. It's not a fully bound nozzle, it's not a round circle, but it's 1/2 of that circle that's creating that nozzle. Well, what can we do then to reduce that drag caused by putting these 2 things together? Horner shows us how to reduce it down to 1/10 of its original value. Okay, I've drawn this on a chalkboard. This, of course, is this, and these 2 lines are represented by these 2. What Horner does is he fills in the area behind the point of maximum thickness on the airfoil here. He fills in the nozzle with a fairing that looks like this. And because he gets out that far, he has to put an after body on it. So he does something that looks like this. All of this area in the nozzle is filled in. Interesting, isn't it? Just about what you'd do at a wing root fairing with a properly designed fairing, filling in the funnel. Okay, let's take a look at something else. This is really interesting. I love this one. Here's Horner again, and here's a little study that I have reproduced on the blackboard magically over here. In this study, they put a streamlined body in the tunnel. This is a body of revolution, it's round, and they put a wing on it. And they looked to see what position fore and aft produced the most interference drag. When they started with the wing way up here, the drag was low. When they moved the wing back, the drag got higher, back, the drag even higher, back, even higher, and right about here, the drag peaked about 4 times as much as it was up here. And then when they moved it back, it got a little less and a little less and a little less until finally back here it was back down to a reasonably small value. The reason everybody knows that when you put a wing on the after part of a fuselage that the interference drag is low is basically because the boundary layer gets very thick back here. Interference drag is not a problem in the back. So when you put a horizontal stabilizer or a vertical stabilizer on an airplane, you don't have to worry too much about interference drag. But right in here, which is pretty close to where you want to put a wing on a normal airplane, the drag is very high. What's going on? The only way I can see that, Horner doesn't talk about this, but the only way I could figure it out was to arrange the drawing so I was looking at it from the top. Here's that wing, nice tapered wing, and if I make a line here that represents the airstream going past that wing, I see immediately a nozzle. Look at that. Here's the thick point of the wing, and from here back it's opening up like mad. There's the drag. So what can we do to fix that? Well, we could put a little fairing in here like this, like we did on the 2 struts, or we can do what I did on the AR-5. We can make the fuselage sides straight, eliminating that nozzle. You have a little bit of a problem here trying to get the fuselage streamlined back down, but it seems to work. So that's it. Big deal. Okay, so here's the straight line. We ran it right from, in this case, right from the vent here, which turns out to be the same width as the fuselage back here. So we ran the straight line right from the vent all the way back to this point right here. While I was filling out the nozzle, I also made a Horner style fairing in here, increasing the radius from the point of maximum thickness on the wing all the way back to the trailing edge. And I also positioned the canopy so that it was filling out this nozzle area all the way back to where it peaks here at the trailing edge. You'll notice that the point where I let everything go here is not all the way back to the trailing edge. The trailing edge is a couple of inches farther back. What I did was I let it all go when the top of this laminar flow wing started to return. It has a little cusp up here, so as soon as it started to curve back up, I let all this stuff go. One more thing, I mentioned earlier that making the chord of the wing shorter helped me to do all this stuff. If the wing had been a much longer chord here, I would have had to carry all of this straight line way back here. So short chord helps. Also, I want to talk to you a little bit about this piece of masking tape here, which represents the exhaust streak. I spent some time looking at exhaust streaks on other airplanes. For example, the P-51. You can see that it goes way up over the point of maximum thickness on the wing and drops way down toward the trailing edge. And you can see that also on the Yak 9 It is also set up about the same way the P-51 is. Both these airplanes have their maximum widths right over the thickest point of the wing, so they have nozzles. The Focke-Wulf 190 is probably the worst example. You can see that the point of maximum thickness on that fuselage is well forward of the wing, and it's tapering throughout the whole distance from the leading edge to the trailing edge, and you can see the exhaust is being pulled well down into the fairing toward the trailing edge. On this airplane, you can see that the exhaust streak is quite high. None of this high peak over the point of maximum thickness, and that, I'm sure, is a result of this business we've done here in the wing root. Okay, let's take a look a little further aft here, and you can see what's happened as a result of reducing this downwash angle as we have. Now it's up here on regular low-wing airplanes. It would be down something like this. It's affected the trim on the airplane in a negative way, as far as I'm concerned. I had spent a lot of time trying to set the incidence on this horizontal stabilizer, and was disappointed to see when I first flew the airplane that the elevator was riding like this. I needed a little more incidence than I have. And of course, as far as I'm concerned, that's a result of having changed this downwash angle here. So obviously what we did at the wing root intersection is having some effect, good in some ways and negative in other ways. That pretty much takes care of interference drag. Let's finish looking at the rest of the airplane. The last thing that all of the experts wanted to talk about that they thought helped reduce the drag of the airplane is the landing gear strut. The first thing they noticed was that it was outboard of the propeller wash. That means that high velocity air coming from the back of the propeller is not striking the landing gear. The other thing they noticed was that we knew how to make good Horner style fairings. We filled in the nozzle back here. It's a little difficult to show you the whole gear right here in the shop because we've had that little mishap. Let's take a look at some shots that we took out in the field. The strut airfoils themselves have a length to thickness ratio of 3:1. Horner says that's just about optimum. And they intersect the wheel pant at the edge of the pant, which eliminates an inside drag-producing corner. The wheel pant itself also has a fineness ratio of about 3:1, and it fits as close to the tire as I thought I could get away with without it rubbing. It's a telescoping spring gear. The pant moves up and down the strut with the wheel. This little scoop provides cockpit air. Can you tell I like P-51s? Altogether, it's a pretty clean airplane. I tried to keep it as smooth on the bottom as it is on the top. You, in our talks, you have pointed out to me that the airplane goes fast, not because of any one thing. It goes fast because of a lot of little things that you've pointed out. Would you mind pointing those out again?
Okay. Yeah, I think first of all, because of your experience in composites, you were able to have the nerve to build a very fast composite airplane. And it's the smoothness that you get with the composite construction that is almost impossible to do in metal that allows you to capitalize on the best of the aerodynamic research on subsonic airplanes that has been done, principally on the wing, getting extensive laminar flow. And you picked a 65 series airfoil. It's been around since World War II, but it's a darn good low drag airfoil. And it has about half the drag of more conventional airfoils if it's smooth enough to actually obtain this low friction laminar flow from the leading edge back to about 50% of corridor further. And we saw with the weight measurements that you are far smoother than you would actually have to have been to, at these speeds, this size of wing, get laminar flow back that far. So you're very likely getting, if you had no control surfaces, you'd probably be getting drag every bit as low as those refined wind tunnel models that NASA ran in the low turbulence wind tunnel and got these drags that were half of conventional values. Okay, now, in putting on the control surfaces, again, from your experience with the sailplane people, you found out very clever ways to reduce any little drag increment from the fact that you have to have an active control surface there. Very close fit at the hinge line on all of your controls, your flaps, your ailerons, your elevator, your rudder. So that has been handled very well too. Then you were extremely concerned about the possible drag increment due to the interference between the wing and the fuselage, as we were talking about earlier. You were showing Horner's book on interference drag, what he has to say about it there. And you did all the right things there. The most significant thing you did was to keep the fuselage cross-section constant width back to the trailing edge of the wing, so that you weren't getting a slowdown of the air on the fuselage, adding to the slowdown of the air on the back part of the wing, and making for problems in the wing intersection. Now, this is most important at high lift coefficient in the climb and between there and CL max, but you have to consider it a little bit too, even at the high speed point. In addition, you didn't just bring the wing in and butt it up against the fuselage. Now, that's a nice right-angled corner, which some of the textbooks say, hey, that's great. But what happens when you have two intersecting plates, or a wing and a fuselage, with an absolutely square corner, is the boundary layer on the wing and the boundary layer on the vertical wall of the fuselage get sucked toward each other into this intersection, and you get a very thick boundary layer buildup, which then is more prone to separating in that adverse pressure gradient at the back end. So your radius in here helps. And this radius of the leading edge softens the deceleration of the air into the stagnation line and gives you a better start on life as we come through here. And then on the back of the intersection, by building that out, you are able to also keep this contraction that this gives a severe slowdown of the flow and the possibility for separation, and then very cleanly handled at the back end of it there too. Now, the thing that really impressed me when I saw the picture in sport aviation was, my God, the thing has got a fixed landing gear. But you did that, the very best that can be done with a fixed landing gear. Number one, you moved it outboard of the propeller slipstream, so it's only seeing free stream dynamic pressure, not goosed up by the propeller slipstream. And furthermore, those very clean struts, which are probably minimum drag struts that you could do within this geometry, are flying at zero angle of attack, because they're not getting swirling flow off the prop and inducing an angle of attack and running your drag off the minimum drag point. Your wheel pants are absolutely minimum frontal area pants, but with good radiuses. So again, it's probably a darn good compromise. Now, I don't know how much wheel was hanging down below, but probably not more than 2 inches, maybe less than that, 1.5 inches. Yeah, in my calculations, I assume 2 inches. So the wheel is very well streamlined off. So you aren't paying the big drag penalty for that. The canopy is very clean lines. I'll fill it again to soften that stagnation region into the start of the canopy, keeping the boundary layer thin, going up over the canopy, and the fuselage in back, even though you started later to taper it, plenty long enough. It's amazing what you can get away on a three-dimensional body in the way of necking it in compared to a two-dimensional wing, and still not have flow separation. So this, and you've done a pretty good job of minimizing the surface area of the airplane. All these things added together, I think, have done it. Now, the thing I didn't know much about until you showed me the plane today was the internal arrangements on the cooling flow. And I would think that that you have had to pay a similar drag penalty, maybe halfway between production light planes that don't do hardly anything to reduce that drag, and the very best that can be done with a liquid-cooled engine, like the P-51. So there's a room, I think, place within your geometry, I think, that could be improved.
And that you think we could fix by turning that radiator around? You think, or maybe making one large radiator over here, and
have fewer 90-degree turns in this flow through here. And also, if you can, within the geometry, do a better job of diffusing the inlet flow through a gradually expanding tunnel to try to get the speed down very low at the radiator face, so that you've converted the dynamic pressure due to velocity into the static pressure at the face of the radiator. So now we've got high pressure on that face of the radiator. We've got low pressure here with this beautiful outlet that you've designed, and will really take the air through there and allow you maybe to reduce the size of both the inlet and the...
You're going to make this airplane go faster.
Oh yeah, I think it's extremely good, and you've done the most important thing already.
Well, that pretty much is everything we know about why the airplane is as fast as it is, why it goes so fast. Thanks to Bruce Carmichael, we certainly know a lot more now than we knew before we started this film. Thanks, Bruce. But speed isn't everything, and one of the reasons that I built the airplane was to have a nice little pleasant-to-fly weekend flyer, so that I could fly with my friends in their midget Mustangs and their T-18 Thorpes. And I have to say that I'm just tickled to death about the way the airplane flies. It's fun. It turns like mad. I outturn everybody. I've got my friend Kit Sodergren in his midget Mustang 4 or 5 times. He doesn't want to do it anymore with me. So it's just, and of course that high turning rate is a result of the high aspect ratio and the low interference drag. Interference drag is also a factor in turning. It just is turned out to be a very comfortable airplane to fly. The seating position is just about right. I lean back at about 38 degrees. I'm not afraid of long missions or any of the rest of that. I'm never cramped in here. It's just about the right size for me. It's pleasant to land and take off, which is one of the things that I was concerned about when I built the airplane. I wanted to make sure, it was actually one of the reasons that I made the gear that wide, is to make it handle well on the ground, and it does. It seems to fly like my old Aeronca. It takes off and lands and tracks just about the same as the Aeronca. In the air, the airplane is quite solid. It surprised me when I first flew it. It doesn't feel like a small airplane. I think a lot of that has to do with the fact that I have very long stick throws. When I designed the linkage, the control linkage, I was thinking about my old Aeronca, frankly, and what that does is it means that in order to make something happen, I actually have to move the stick. You don't just think about it like you do in some other airplanes. No twitchiness here at all. The control forces seem to be very well harmonized. I was surprised to see that the ailerons are as light as they are. They're very powerful. The roll rate is very high. Surprisingly high, as a matter of fact, considering that it's got a long wing. It's about 130 degrees a second, I believe. No PIOs. The pitch stability is quite good, so that helps on approaches and landings. The airplane does great loops, something I've just started to do. I'm not really an aerobatic pilot, so high-performance airplanes are new to me. The airplane stalls at about 56 miles an hour clean and about 53 miles an hour with full flaps. Flying behind a two-stroke is a little different from four strokes, at least, in that the first thing you notice is that each time you throttle back to descend and therefore unload the propeller, the exhaust gas temperature gauge goes crazy. Apparently the mixture gets very lean at low throttle settings or at low load on the engine, and the only way I've been able to cope with that in long descents is by using the primer pump to add a little fuel, basically to cool it with fuel. That gets a little old. There has to be something better worked out for that. On long descents, my thumb gets tired, 4,000-foot descent. The other thing, of course, that we've already mentioned is that the airplane has very low torque at low RPM. The takeoff RPM on the airplane is 4,400, which is just about 38 horsepower, which is not a lot of horsepower, not nearly enough to get the job done. I generally cruise the airplane at a true airspeed of between 165 and 175. That's limited really by the noise that's created when I get the RPMs up over about 5,600. At 5,800, the noise in the cockpit gets very loud. But all in all, I've had very good experience with the two-stroke. It's been a great little engine. It's light enough to make this rather heavy airframe a light airplane, and I can hardly wait to get it running again. All right, we're just about to wind this thing up now. Before I leave you, I feel like I just have to tell you about all the books that I've read to get this thing done. You know, I'm not an engineer. I had to find books that I could understand, which is not that easy. The first one that really set me off was this study by B.J. Holmes and C.J. Obara on natural laminar flow. It was an interesting study for me because one of the airplanes they studied was the Amsoil Rutan Racer, which I mentioned I'd worked on. Basically what this study showed was that with composite construction, it was very easy to get the kind of performance in real life that they could get on these long laminar flow run airfoils in wind tunnels. And it happened that I was right there when they did the study on the Amsoil Racer, and I saw with my own eyes that they were getting laminar flows right back to about 60% of the airfoil. And because I had built much of that airplane myself, I felt very confident when it came time for me to pick my own airfoils that I could get the same kind of laminar flow performance that they did. I got the airfoils themselves out of Theory of Wing Sections by Abbott and von Duynhoff. This is a real standard book. They talk about all kinds of stuff, anything to do with airfoils in this book. High lift devices, flaps, slats, lots of talk about laminar flow airfoils. And in the back of the book, they have airfoil after airfoil and the performance of each of the airfoils, as well as once you've picked out an airfoil that you like with the lift curve slope and the drag that you like, you can flip forward a little bit here, and they'll show you what the ordinates are so that you can loft the airfoil yourself at any length and any thickness. It's a great little book. Can't really design airplanes without this book. For all the rest of the drag reduction stuff, I used Horner. This is my favorite book, Fluid Dynamic Drag. Horner actually has written two books, Fluid Dynamic Drag and Fluid Dynamic Lift. This is the one that I really get a kick out of. It's got everything in here. He talks about how to reduce the drag of bridges and trains and cars and buildings. And really, you don't have to be an engineer to read Horner because it's full of pictures. And next to every one of the pictures, he shows what the drag of that particular thing is. It's just wonderful stuff. I like this book so much, I take it with me on vacations. Here's some stuff, for example, on underwing stores. This is typical because on each one of these cases, Horner shows you the picture of the thing, and then right next to it shows you what the drag is. Right next to this one, there's the drag, there's the drag, there's the drag. So you can make comparisons without even hitting your calculator. This is a wonderful book. You can see how dog-eared it is and thumbed through and indexed. I put myself to sleep at night reading this book. Thank you, Mr. Horner. For all the rest of the stuff, the nuts and bolts of where to put the wing and how big to make the tail and all the rest of that, I use Light Airplane Design by Ladislao Pasmini. This is also an excellent book. Basically, it shows how he designed his own airplane. It's all applicable to low-wing airplanes, and he shows how to arrange the landing gear and all kinds of interesting stuff in here. Great book. One of the original series of books that I got that really showed me the nuts and bolts of engineering was this series put out by the EAA Air Museum. I made reference to this when we talked about Mr. Parker and his studies on interference drag. These books are basically a compilation of old magazine articles put together by Paul Poberezny, and they're just full of interesting stuff. How to design airplanes. Last, for all the materials and lots of other stuff, lots of good information, Aircraft Spruce and Specialty Company's catalog. Aircraft Spruce is in El Segundo in Southern California, and this thing is full of every kind of material you'd ever want to see. You can buy fuel tanks and tires and engines and paint and everything in the world in here. Lots of composite stuff in the early part of the book, and as well as books and lots of other good information in the back. If you live in the eastern part of the country, Wick's Aircraft Supply in Highland, Illinois, you'll have to look that one up. And that about takes care of all of this stuff. Hope you've enjoyed this. We certainly have. And we'll see you in the next movie.
Church, armed only with a kitchen knife, a crosscut saw, and some sandpaper, Mike creates the master patterns for a state-of-the-art Formula One air racer. Starting with a pencil drawing and a small foam model, he covers the lofting of full-size cross-sections, the carving and finishing of the plug, and finally, the assembly of the airplane with its finished molded fuselage. Making fiberglass molds chronicles the development of a 6-part molded fiberglass cargo pod. It shows all the design and fabrication techniques used to produce low-cost, professional quality production molds. Every step is explained, from first sketches, through master patterns, to male and female molds with offsets and joggles, to finished parts.